I'm Bridget Johnson from Lexington, Corrynn, Breidinger from Purcell, and I'm not even going to try Uysal's last name.
Yeah, it's from Tulsa.
And he is from Dove Science Academy in Tulsa. We were in the FEARS lab with Dr. Vemuganti, and we had 2 lab assistants, Sijan and Ollie, and I am also not going to attempt their last names. So what we were looking at is fiber reinforced polymers, also known as FRP. It is used in a variety of different applications. It's a fiber reinforced polymer, a composite of a material with a polymer matrix to reinforce different fiber types. We have some examples here. This is what we're talking about, kind of. It is this material with a epoxy polymer holding it together, and I just liked the way these looked after the epoxy dried in the cup, so I took one. And it's used in airplanes, which we have an aviation teacher in our group, but also that is how they reinforce wind turbine blades. So there are a lot of different applications. They have tested in the lab some carbon, rebar, and glass-based rebar fibers and fibers used in storage tanks, used in all different applications. And we did get the opportunity to look at some fiber-reinforced concrete samples in the lab too. In terms of strength, FRP is stronger than steel. However, it does not have ductility, meaning it cannot bend the way your steel rebar can bend. It breaks easily instead. So the growth of FRP has been hindered in infrastructure applications because of that. FRP is not a fail-safe material because when it fails, it breaks, and it fails all at once typically. So we were looking at ways to add some stress-strain behavior to that so that it doesn't have a catastrophic failure all at once. Steel is very ductile, so usually they can avoid, even though it degrades over time, they can avoid the brittle break that happens. So to overcome some of the shortcomings of FRP, there are a few different hybrid composites that they use: interlayer, intralayer, and intra-yarn. A linear breakage pattern looks like that. You get strength as you're testing it, and it suddenly drops off. What we are looking for is the characteristic load drops of successive fractures of patterns that are at different angles or mixed together of materials. Pseudoductility is a flat-topped stress-strain curve on a monotonic tensile test up to failure. If it's ductile, you get that big break, which could cause some sort of an infrastructure failure all at once. Let's see. So this just shows you the FRP composites with a monotype fiber or a single fiber. As it stresses, your carbon is actually the strongest material, and then you have glass reinforcement and steel, which is not as strong, but it doesn't fail as suddenly also. So the hypothesis, and this is actually from Dr. V, is engineering shared stiffness between different layers of an FRP composite by designing fiber layer thicknesses and orientations in some sort of a stacking sequence will cause a gradual failure so we don't have a catastrophic situation. So there's a few different ways to do that. 3D printing is fairly new to the game in this. 3D printing, they can do fused modeling where the 3D printer would melt the fibers and the plastic together and run them through, or you can have it separate, which is what the 3D printer we used, where, if you can see here, we had a thermoplastic polymer and a continuous fiber on two different spools that have two different nozzles on the printer. And then for every 1/10 of a millimeter layer, we could tell it whether it was doing the nylon between the layers or doing the glass fiber, and at what specific angle it should print it. And that kind of shows you how it would wind through the two separate nozzles. This, I think, was supposed to be a video, but it doesn't play, but it does kind of show you a close-up view of the two separate nozzles on the printer. And an individual layer can be selected and reinforced with different orientations of fiber. As that shows there, you can see there's several different angles and orientations being printed. I'm not sure. The accuracy is super high. As you can see, 98.6 to 99.9% accuracy from the 3D printer. If you're using what we call a wet layup method, which is most common now, that's what we saw when we toured a windmill plant. It's where you're manually infusing a fiber with the polymer. When you go to cut this, it's really hard to try to get it exactly a 12-degree angle. And so the 3D printing is far more accurate on those angles. And I think this is where we were switching.
Yeah. Okay. In the wet layup application, when we got the fabric, it can just shift easily. If you use a little bit force, as you see, all the angles just changed. So the accuracy is so hard with doing the wet layup application. So instead of that, what we are using is here the 3D printer, because as you see, we wanna just print the 12 to be is 12.16, which means the 98.6% accuracy. So the 45, as you see, the 45.03, which means 99.93, actually, we can say. So just I want to talk about a little bit our machine, because it's important and it's really good machine, because it's just the print, each layer is a 100 micron. For the 3D printer is really so thin material. So as you see, the printer temperature is 275, and actually it's melt the fiberglass and give the shape. It's so thin, and with the correct angle, it's really good for us. And if I have to talk about the machine here, our fiberglass, and this is our bed, and this is the exact rudder, and we have two nozzles here. If you can see from down, we have the plastic nozzle and the fiber nozzle, thermoplastic and fiber nozzle. And every time when you try the print, it has to print first of all the nylon thermoplastic as a bed. Then it's just print our fiberglass on it, and which angle do you want? And at the end of it should just make a roof of the thermoplastic. So here we have some problems about it. I'm going to talk about it. But as you see, this is the 3D print, the composite application. We give the angles, and the empty part actually filled by the thermoplastic again. Then the thermoplastic and the fiberglass bond each other exactly in a good way. So this is not we wanted, because when the fibermetric interface, the load, so this force, the load force, make the how can I say, the fiber reinforcement composites subjected the tension tensile loads, the force is transferred to the fiber, and shear stress shown in figure, guys. So this makes the catastrophic failure because they are not separated. They together, they bond each other. So if the first one is just get failure, the others failure after that. So this is not we wanted, and we need to find the method, and this is the kind of the things they make the failure together, the fiber pull out, fiber bridging here, the second one in the third one, the fiber matrix debonding, and the fiber failure, and we have the matrix cracking too. So this is what we want. We want to separate each layer. So if the first one failure, the second one's not going to fail because there is no bonding and the force can affect the other one directly too much. But if we bond like the fabric, if I touch the first part, this part, and I apply the force, what happens? This part gets a tension, this part gets relaxed. So if started here this from the beginning, it's going to continue all over the way. So if we separate, if we give a gap, they don't affect each other too much. And in our test, we use different angles in our specimen. Guys, we have just the different 0 degree, 6, 12, 18, 24, 30, and 45. But in our test, we want to use both methods together, the wet layup and the 3D printer. So we have some difficulties about that because our fabric is the 90 degree base fabric. We have the angles that we can use just 90 degree, the horizontal and vertical. But our machine can make 180 degree, which is really good for us. So in here, as you see, this is 12, 24, 30, 45, and we make the symmetric of that. For example, 12, symmetric of the 12 is negative 12, which is 168 degree. So they symmetrically support each other in the machine, but when we try and use our fabric, it's already inside it, this is 90 degree and support each other. So we can use just in the 0 degree or 45 degree in our slide, as you see still. We cannot make a 6 degree or 12 or 18 degree. So in our specimen, we use the wet layup with the 0 degree and the 45 degree. The others just 3D printed, but as I told you, we want them to bonding each other, we want to debond each other. In here, Dr. Vemuganti tried a way, just when it's printing, stop the printing and put the dry ice, try the cold, and reprint and resume. And without debonding, and they just not connected, then they do not fail together. It's not a catastrophic failure, so it's not work, I think, because you have to stop and fill all the part with the dry ice, wait to get cold. So we try to find different methods in here. Just Dr. Vemuganti made a test with different angles, as you see, different colors in the concrete, and she tested, but this is the problem. We want to solve the problem with different methods. Instead of using dry ice, when it's 3D printed, it's 3D printing, we want to put different materials inside, then we can debond easily, which is aluminum foil and the parchment paper. So the parchment paper immediately failed due to the inability to create adhesion, even the glue applied, which means nothing can stick on it. Instead of this, we used the aluminum foil, and the thickness of the aluminum foil is 20 micron, which is the machine makes 100 micron, it's thinner than the machine made, so we can apply easily, but we forget if we make a lot of layers, the 20 microns really make sense. At the same time, we put some glue, so it works, but you have to adjust the level of the 3D printer every time, so it's not useful method. So we are thinking the new one for now. And
okay, so this was our failure. We didn't realize how thick the aluminum foil was when we started, and so the first print did not go well, so Yuysal manually adjusted for the second print, but it's really not practical. So that brings us to our third method of testing. We decided to do a combined testing. So we did a wet layup where we used one layer of the glass fiber, a layer of carbon, and another layer of the glass fiber. And from there, we picked the easiest angles to cut manually. So we did one piece for each sample at the 0 degree and 2 pieces, one for each end, because it's got to be symmetrical all the way through, at the 45 degree angle. So got our protractor out, our nice, pretty straight cuts. Again, when you're working with the fiber and you're applying epoxy, it does have a tendency to shift, which can affect your angle measures. So our combined method, we had a lot of layers. This is a picture of us with our separate pieces, putting them together. So we had our 3D printed pieces in between our wet layup pieces to give us some very, very thick coupons, which we then attached our tabs to so that the machine could hold on to it when it was tensile stress testing. So we used wet layup for our 45 degree angles, 3D printed our 30, 24, 18, 12, and 6, and then another wet layup for our 0, and mirrored it on the other side. So we came to testing day. This is the machine that we used. We had 3 samples to test. Our first test, the way we had it clamped in the machine, it was a little bit too far on the ends because our sample's so thick. It didn't have a good grip, and our bonding of our tabs kind of failed before anything else. So for the second test, we adjusted and put our grips down a little bit further.
I didn't know if we had a slide that showed that. Do you want the results?
We can do the results. And so this was our first test. This is kind of where the sample just came apart somewhat. For our second one, we had some failure in the middle of a few of our 3D printed, but it wasn't really what we were looking for. There were a few steps, but not the transfer of load that was the real intention behind it. But our third test was successful. And you can see the graphs that Bridget went over earlier. Once the first failure occurs, the forces are then transferred to the next one, and that's where it picks it back up. And so you can see that by our peaks and our fully destroyed sample. So it was successful, and then it was able to transfer the forces so it didn't have that catastrophic failure all at once. So it makes it safer, gives you a little more time to address the problem before, before it becomes an even bigger problem. So we were pretty happy with our results. I mean, we went through a lot of different iterations, got to really experience real research because we weren't exactly sure how any of it was going to work out. So we tried, we reevaluated, we tried again, we reevaluated, to get to the point where we were able to have a successful test. And I have to say this was an incredible experience. We had a lot of fun out in Fears Lab. There's a lot of great work going. We've got a good picture of Sijan and his carbon fiber reinforced concrete block that did not break. It did not completely fall apart like we were hoping. Well, I was hoping for. He was not hoping. He was very happy with.
Blow up in there.
He was very happy with his results. And that sort of thing is they are working really hard to increase the safety of our roads and bridges and making huge progress for everybody. This is the process when we were testing. He tested glass fiber and carbon fiber. My little Lego guy with the extra concrete. And then a huge piece of bridge that they were working on. I got to see some sparks fly, so that was pretty cool when they were cutting the rebar. But just concrete 3D printer, there's some just really cool, really exciting cutting edge stuff going on. As making our very own wet layup, that was really neat. Compression testing on concrete samples. So there's a lot of stuff going on out there, and the main goal is to improve safety. So we just want to thank Dr. Nanny, Dr. Tessman, Dr. Vemuganti, and then Ali and Sijan have been putting up with us all summer, and they have been absolutely amazing and so helpful and given us some really exciting experiences. And last but not least, Joe, who has facilitated everything. So thank you guys.
Yay!